certain layers of rock underneath the crust. Most of the earthquakes have occurred along the boundaries of these plates. Main seven plates, that is Pacific plate, North American, South American plate, Eurasian plate, African plate, Australian or Australian plate, and Antarctic plate. And there are many minor plates like Philippine plate, Cocos plate, and so on. And if you look at the frequency of occurrence of earthquakes, earthquakes are measured using magnitudes here. Magnitude indicates the amount of energy release at the source, which are shown here in the red. Strong earthquake magnitude 6 to 6.9, around 134 in a year. Major earthquake 7 to 7.9 magnitude, around 17 annually. And great earthquakes magnitude 8 and higher, at least one somewhere in the world. And there are very minor earthquakes which are mainly recorded by instruments. We may not feel it, but it will indicate the seismicity of the region. And these circles indicate the occurrence of earthquakes. So you can see most of the earthquakes have occurred along the boundary of the plates. And this is our country, India. So most of the earthquakes here. And Japan entirely covered by earthquakes. Some of the greatest recorded global earthquakes, magnitude 9.5, 1968 occurred in Chile. And 1964, Alaska, magnitude 9.2. Indonesia, 9.1. This is actually in India also. A lot of damage occurred in southern part of India, Tamil Nadu coast, Kerala coast, and so on. More than 2 lakh people died during this earthquake. Then magnitude 9, 2011 Japan earthquake. More than 15,000 people died, and so on. So magnitude more than 7, causing lot of damage here. For example, 2010 Haiti earthquake, more than 2 lakh people died, magnitude about 7.1. And if you consider our continent, Indian continent has moved and collided with the Eurasian plate. And even now, Indian continent is undergoing, moving under the Eurasian plate. And many great earthquakes have occurred along this Himalayan belt. This region, these years actually show the occurrence of these earthquakes. And some earthquakes away from this plate boundary also, which we call intraplate earthquakes. For example, huge earthquake, January 26, not 2000, 2001. This shows the seismicity of India since 1973 to present. All these red circles indicate the occurrence of earthquakes, even including minor earthquakes. And the right-hand side, you can see the tectonic map of India. And this is the plate boundary or boundary here. And we have these red lines. They indicate actually fault zones, which are away from the thrust boundary. There are many fault zones all over India, and many earthquakes have occurred along the fault also. Some of the largest Indian earthquakes are listed here. 1618 Bombay, not sure about the magnitude, around 2,000 lives lost. Then 1720 Delhi, magnitude 6.5. 1819 Kutch region, Gujarat, magnitude 8. 1828 Srinagar, magnitude 6. 1833 Bihar, 7.7. 1897 Shillong, magnitude 8.7 earthquake. So entire northeast comes under severe seismic zone. Then 1905 Himachal Pradesh, magnitude 8, and so on. 1934 Bihar Nepal earthquake, magnitude 8.3. And we look here, 1950, Arunachal Pradesh, China border, magnitude 8. And magnitude 6.8 earthquake, Chamali earthquake in Uttarakhand, 1999. And 1997, we had Jabalpur earthquake, 1993, Latur earthquake, 1991, Uttarakashi earthquake. All these earthquakes, a lot of masonry structures got damaged. 2001 Bhuj earthquake, magnitude 7.7. Then 2004 Indonesia earthquake, magnitude 9.1. 2011 Sikkim earthquake, magnitude 6.9, and 2015 Nepal earthquake, magnitude 7.8. Indian continent earthquake, so Nepal earthquake also listed here. If you look at the seismic zoning map of India, as per IS 1893-2016, our country is divided into 4 seismic zones. Seismic zone 2 to 5. Earlier there were 5, but zone 1 is merged with zone 2 after the revision in 2002 after the Bhuj earthquake. So zone 5 indicates very high risk zone here, Kutch region, parts of Kashmir, and here, UP, Bihar, and the entire northeast. We can expect magnitude of 8 and greater. And zone 4, shown here in green color here, high risk zone, magnitude up to 7.9, magnitude 7.9. And then zone 3, shown in yellow color here, we can expect earthquakes of magnitude up to 6.9. Then zone 2, seismic disturbance up to magnitude 4.9, low risk zone. Zone 3 moderate, zone 4 high risk zone, zone 5 high risk zone. So about 60%, 58%, or almost 60% of our country, we can say that it comes under moderate to very high risk zone. So it is very much essential that we consider earthquake resistant features while designing the structures. This shows the effect of soil on the characteristics, on the vibration characteristics of building. This is the source of the earthquake, fault rupture, or the place, point where the rupture starts, point of energy release. So waves we travel, earthquake waves or seismic waves we travel within the earth, we call body waves or deep waves. And waves we travel on the surface of the earth, we call surface waves. So if this is the point of interest, these waves travel through within the earth, then after reaching surface, travel along the surface of the earth. And when they travel within the earth's interior, depending on the soil conditions, the seismic waves get amplified. As you can see in the right-hand side picture, this is hypocenter or source of the earthquake. This is a seismic wave. And when it passes through soft soil, the seismic waves get amplified. So the buildings located on soft soil without proper foundation details may experience heavier damage. Thus, earthquake waves travel hundreds of kilometers within the earth and few kilometers through soft soil, but soft conditions. So these waves get more amplified when they pass through soft soil, and structures may get damaged. Shaking record is shown here. We call the seismogram, the record of the ground shaking. So body waves are further classified as primary waves and secondary waves. So first primary waves reach, then secondary waves, then surface waves. surface waves. If you look at the amplitudes here, this the surface waves amplitude is considerably higher than initial primary waves or secondary waves. Most of the damage is caused when these waves reach the building. So this we call strong motion. The part of this seismogram which is causing the damage to the structure. So this look at the it's random in nature, of course time dependent and also cyclic. A typical earthquake record is shown here. This is from the Bhuj earthquake, 2001 Bhuj earthquake. This is the acceleration history, acceleration in terms of the acceleration due to gravity. So surface waves, primary waves, secondary waves, and body waves, then surface waves, and with the passage of time dies down. This total record for 140 seconds, so around 2 minutes plus, and this is the displacement time history. More than 10,000 people died during this earthquake, and if you look at the time, it is only 2 minutes. The entire quake lasted less than 2 minutes, and if you look at the strong motion, this is around 30 to 60 seconds region. If you look at the damage all over the world, 1900 to 1949, around 7,95,000 people lost their lives, and a major portion is due to collapse of masonry building. Most of Asia and even in Europe, Latin America, South America, there are a lot of masonry buildings. Then this is collapse of timber building, very few RC building during that time. Then fire, post-earthquake fire hazard, landslide, and then other causes. And if you look at the data 1950 to 1999, still a major portion of fatalities is due to collapse of masonry buildings. Timber buildings are, number of timber buildings may be less compared to earlier stage, but RC buildings have increased. So damage due to collapse of RC building has also increased. Then fire following earthquake, landslide, and other causes. So majority of buildings all over the world are made of masonry and RC, and it is very much essential we include the earthquake resistant features in these buildings. Seismic performance of buildings during fast earthquakes. We will go through these now. Initially, I simply introduce a few slides about the seismology aspects. Typical failure patterns identified in masonry building. Failure at the junction of two orthogonal walls. If you look at this is in one direction, this is perpendicular direction, and failure here. Unreinforced masonry building, 2010 Sikkim earthquake data. And combination of in-plane and out-of-plane failure in Samkyali during Bhuj earthquake. This also two walls particular here. These masonry walls failure has occurred. X cracking, development of X cracking during northern Iran earthquake 1990. Masonry collapsed here. Here separation of wall at the junction of two walls. And then this is an example of failure of stone masonry wall, buckling of plates. Actually, when we construct stone masonry, two layers of these stones are kept, And to increase earthquake resistant features, we are supposed to provide keystones running through the full width of the wall. If they are not sufficient, we can expect these kinds of. And this X cracking, this is because of the alternate development of tension and compression alternatively along the diagonals, and this results in these kinds of walls. In masonry wall, we can improve the earthquake resistant features by providing wooden or RC beams, which we call bands, at plinth level, at lintel level, and so on. As you can see in this right-hand side building. Good performance due to lintel band and plinth band, whereas a building with no such bands has failed here. This is from 1993 Latur earthquake, central India. One masonry house in Kilari village had horizontal lintel band performance. The cracks developed in the walls, but they could be repaired easily by providing by a grounding. This is gable roof. In this case also, we provide these bands at plinth level, lintel level, and then provide proper connections in the walls. So we can improve the earthquake resistant features by providing these simple methods. This is wall flexure, failure of the wall, bending in during Bhuj earthquake. Partial collapse of stone masonry walls, you can see here. This is Uttarakashi, 1991 Uttarakashi earthquake. Similar damage, you can see out of plane failure of wall in Bhaktapur city during the 2015 Nepal. So masonry structures here without bands. Following typical damages can be identified in a masonry building. This is the direction of seismic action. So this is in plane and perpendicular this is here we can see out of plane bending, out of plane bending. Then these diagonal cracks or shear cracks. And then we can also expect wall fracture. Following typical types of damage: cracks between walls and floor, cracks at corners and at wall intersections, out of plane collapse of perimetral walls, diagonal cracks in structural walls, partial disintegration of or collapse of walls, partial or complete collapse of buildings. The figure below shows the deformation and typical damages suffered by a simple masonry building subjected to earthquake down motion. These are some of the failure pattern which we can expect in a masonry building. And this I explained earlier also. By providing these wooden beams or what we call bands, wooden or RCC beams at particular intervals, and by a good connection between roof and wall, we can increase the earthquake resistant features. This figure shows essential requirement to ensure box action in a masonry building. Walls with small openings, good connection at the wall corners, good connection between walls and foundation, and of course plinth band and lintel band. Now about RC buildings. Earthquake resistant design seeks to produce structures that can withstand a certain level of shaking without excessive damage. Total horizontal earthquake force in a building increases downwards along its height. So inertia forces increase along downwards along its height. This is a collapse of the building. The difference between gravity load and earthquake load is shown here in the right hand side. So this is the gravity load. So this is the deformation shape. Stretching of members and location of tension. These are the areas where we expect tension and we provide reinforcement accordingly. Whereas in the case of earthquake load, it can be from left to right and then right to left. So the location of tensions, if you look here left to right, these are the areas of tension development. And these are when the force is from right to left. So these get reverse. So we need to provide reinforcement on both faces of the members, when we consider the earthquake load. This can be anywhere in India. RC walls, reinforced concrete construction with unreinforced masonry infills are most common in our country. And during 2001 Bhuj earthquake, 132 such low to medium rise structures collapsed in city of Ahmedabad itself. Soft story collapse of the right wing of the building. This is actually at the same level. It was at the same level. However, in the ground story, you had opening for parking or some other purpose. So this ground story has collapsed because of the low stiffness. Such a failure we call soft story failure. So you can see this water tank columns have. The left wing without soft story is apparently undamaged. So here you can see the wall. So open ground story or soft story, if you consider a building ground story open and all the higher stories we have the masonry wall, so this will be the deformed shape. So the ground story columns are subjected to large deformation. If you analyze without infills, this would be, as a bare frame, this would be the deformed shape. However, because of the infills, the ground story columns are subjected to large deformation. Open ground story buildings with masonry infills only in the upper stories. Severe deformation demands at ground story columns. So, in such a case, the ground story columns get crushed. To avoid this, we take care while providing reinforcement with the ground story columns, and also we provide stirrups at closer intervals. So, failure of such a building, collapse of apartment building in Ahmedabad, open ground story collapse. Right hand side also you can see this is Gandhidham, a hotel called Sayaji Hotel. We are seeing here first story and above. The ground story has been crushed. This is closer view of ground story columns. So this is open ground story or soft story failure. This is also from Bhuj earthquake. Short column effect. Unreinforced masonry infills placed up to partial height. Adjoining the columns reduce column height. So these are the columns here. Because of this masonry infills up to partial height, these portions becomes short columns. And these are subjected to shear failures. To avoid this, we provide stirrups at closer intervals. This portion of the columns. Then this shows bare frame. In the case of bare frame, predominantly frame action bending here. However, infill frames predominantly shear action. So when subjected to quake-induced forces, alternate compression and tension along the diagonals, and this results in this kind of cracks. And when they exceed the capacity, we can expect the walls to fall down, as you can see here. This is from the 2016 Manipur earthquake. Then this photograph is from the Bhuj earthquake. Failure of the weak concrete in the toppy portion just below the beam. If you look at the schematic diagram here, When we do the concreting, we do the concreting for the column here. And then top portion of the column and these beams we do together. This portion, 10 to 20 centimeters or 100 to 200 mm, we call this topi. Concreting in the beam and the topi is done together. However, because of the reinforcement here, flow of concrete through bottom beam bars is difficult. Proper compaction has to be done. Otherwise, there can be honeycombing of concrete in this portion. And when subjected to lateral loads, like earthquake-induced loads, then we can expect these kinds of failure. Here also, crushing and spalling of concrete close to the beam bottom. Then shear cracking of non-ductile columns of an open ground story buildings. You can see this is a ball pen here. So the spacing of stirrups is more than 150 mm center. And in this building, we don't see any stirrups at all. The code specifies 135-degree hooks, and also this length is also specified 10 times the bar diameter. This is when the cross section is less than 30 centimeters or 300 mm. And when it is more than 300 mm, it is recommended to provide these kinds of cross ties. So by providing these 135-degree hooks and then at closer intervals, can avoid of shear failures. Also from Bhuj earthquake, damaged school building in Pukuma village. Closer view of this beam column joint is shown here. The reinforcement has just come out. Reinforcement has just down. The code specifies in an external joint, we have to take the reinforcement, development length plus 10 times the beam diameter. This top reinforcement and bottom reinforcement, same thing. And if this is not done properly, we can expect these kinds of just pulling of the. Then this is also from the Bhuj earthquake, reinforced concrete warehouse at the Kandla port. This is the warehouse building. Exterior columns got damaged. Damaged perimeter columns between window openings on the ground floor. The interior columns performed well. Perhaps these columns are subjected to large the shear force. Then this shows how buildings twist during earthquakes. It's taken from earthquake tips, IIT Kanpur earthquake tips. Rope swings and buildings both swing back and forth when shaken horizontally. The former are hung from the top. You can see swings are hung from the top, while the later are raised from the ground. So like single-story building, three-story building. If the length of these ropes are uniform and if the column heights are uniform, and when subjected to earthquake ground motion, we can expect uniform movement of floor. Identical vertical members placed uniformly in plane of the buildings cause all points on the floor move by same amount. This is the original plan. Here this is the distorted one. So all columns move by uniformly by same amount. When we have cases like this, one side is heavy in the building, like in a swing, say the child is sitting on one side. So this will result in twisting. Same thing is happening in the case of building. Even if vertical members are placed uniformly in plan of building, more mass on one side causes the floor to twist. Similarly, when the roofs are of unequal height, then also we can expect these kinds of twisting. If you compare this with building on slopy ground. So some columns are of longer length compared to these columns. In such a case, we can expect twisting. So vertical axis about which building twists. Buildings with wall on two or one side in plan. In this case, we have walls here, and in this case, walls on one side. In such a case, also we can expect twisting, torsion. Buildings have unequal vertical members. They cause the building to twist about a vertical axis. This is actual failure due to torsion. And this is a plan of a building called Mansi Complex, 2001 Bhuj earthquake. If you look at the plan here, this is the standing portion. This is the collapsed portion. There was a swimming pool on one side at the top, at the penthouse level. So center of mass didn't coincide with center of rotation. There was this much eccentricity, and when subjected to earthquake-induced motion, so there was torsion, amplified torsional response. So this side collapsed, and it also hit the adjacent building. Direction of movement of building just before collapse. So adjacent building also got damaged. So this is standing. So in this photograph, we are seeing one side of this building, this standing portion. The other side has collapsed. In the case of multi-story building, even single-story L-shaped building or U-shaped building, by providing joints, we can make it simple rectangular shapes. Actually, I was involved in this Bhuj earthquake damage survey. This is me, 2001, 20 years back. Then 20 years back, IIT Roorkee professors were there, and some Japanese team had also come. So together we listed, and most of the photographs which I showed taken by myself. Now we'll go to some earthquake examples around the world. This is Valdivia earthquake, 1960 in Chile, magnitude 9.5. So far, the largest recorded earthquake, magnitude 9.5. That is 1960. Valdivia is a city that was founded as early as 1552 by Spanish explorers. It is also called as City of the Lake. And the 1960 Chilean earthquake, the largest event in modern history, and experienced three distinct hazards due to this earthquake: strong ground shaking, tectonic subsidence, and tsunami inundation due to tsunami. The focal depth, the point of energy release, 33 kilometers. So we call this shallow earthquake. If it is less than about 50 to 70 kilometers, then we call shallow earthquake. And there can be a large damage due to shallow earthquake. This is the South America. This is Chile. And due to this 9.5 magnitude earthquake here, tsunamis were generated. So tsunami movement is shown in hours after start of tsunami. So for example, this is 10 hours, 12 and so on. It reached Hawaii in 16 hours. Then after 20 hours, the tsunamis reached even Japan, Philippines, and so on. So in this earthquake, roads, ports, urbanization, dwellings, school, water treatment plants, and river banks suffered the effect of liquefaction and lateral spreading. You can see cracks develop and lateral spreading. So a lot of damages occurred for the buildings near the coastal area. Here you can see the depth of lateral spreading. Person is standing. The city is underlain by interlayer sand and silts, having moderate to high plasticity. The surface topography of the city has been modified over time. Low spots filled by low and high plastic silts experience ground failure. Some of the damages to buildings. Damage occurred in unreinforced masonry structure in Concepcion region. Damage to RC bridge deck on this river, Bayo River, and damage caused by subsidence grounds. So those are the photographs. 1960 Chilean earthquake. This is 1964 Alaska earthquake, magnitude 9.2. This is so far the second largest earthquake recorded, magnitude 9.2. Lateral spreading caused distortion of the railroad tracks in Prince William Sound, Alaska. Right-hand side shows the steel truss railway bridge across the Rio Bananito, located in the foothills about 20 kilometers inland. Lateral spreading of the banks destroyed the caisson foundation. The caisson foundation supporting this structure has been destroyed, and the bridge and allowing it to drop on the banks. In 1964 Niigata earthquake, magnitude 7.3, magnitude is relatively less compared to other earthquakes. Some of the four-story buildings in this Kawangi Shichijo apartment complex settled and tipped as much as 60 degrees. Loss of bearing strength was caused by liquefaction of a sand layer 10 to 15 feet, that is 3 to 5 meters below the base of the affected buildings. The peak ground acceleration did not exceed 0.1 g in the earthquake. So the earthquake itself was not so severe. However, because of the liquefaction of sand layer below the foundation of this building, resulted in tipping of the buildings. So after this Niigata earthquake, the geotechnical earthquake engineering became an important field of study, and people try to understand the requirement of foundation designs to prevent the failure of the structures. This is damage 1971 San Fernando, California earthquake, damaged section of freeway overpass. You can see here. Here also piers collapse. Failure of San Diego freeway overpass. This earthquake reinforced the need for bridge designers to consider strong ground shaking as well as ground failure. And during this earthquake, a dam also got damaged. Aerial view of a collapsed section of the lower Van Norman Dam. So any failure of the dam result in large secondary disaster downstream of the river may get inundated. Failure of structures, you can see damage to the columns, shear failure. Second story column fracture of Olive View Hospital. This Olive View Hospital, which got damaged during this earthquake. Collapse first story of psychiatric building at this hospital. Fractured column. This is fractured column of Seaway underpass. 1985 Mexico earthquake. Mexico earthquake is also reinforced the effect of the liquefaction, and also the magnification of seismic waves when those waves pass through the subsoil. Mexico earthquake struck at early morning on the 19th September 1985. The earthquake occurred with a magnitude of 8.1 and maximum intensity of 9. The city suffered major damage due to the large magnitude of the earthquake and also the ancient lake bed that Mexico City sits in. The epicenter of the earthquake is quite far from Mexico City. You can see here. The plate boundaries that Mexico coastal area has is of the destructive plate boundary. One plate subducting over another plate. This is Cocos plate. And this plate is moving under this Mexico plate. Cocos plate is subducting North American plate at a rate of 5 to 7 centimeters per year. Same thing is shown here. So let us see the movement here. This figure 1 shows Cocos plate moving downward, and this is North American plate. Upper plate is acting like a spring. And here in the second figure, both the plates are getting locked due to friction. And strain energy builds up here, shown in the red color. Due to locking, energy is getting stored in the fault line, and then there is sudden release, resulting in earthquakes. After some time, upper plate overcomes friction, and sudden release of energy takes place, resulting in the earthquake. So this is what happened here. And Mexico City is about 350 kilometers from this point of rupture or epicenter of the earthquake. Mexico City area was 350 kilometers from the epicenter, but still it caused widespread damage in the city. If the ground conditions are uniform, if this is the shaking here at the start, if you move away, for example, this is at 13 kilometers, 27 kilometers, 50 kilometers, and so on, the values decrease, go on decreasing. If seismic waves were traveling through uniform material, ground shaking would be half as strong at 13 kilometers, 1/4 strong at 27 kilometers, and 1/8 as strong at 50 kilometers. So at 50 kilometers, it would be 1/8 of what it is at the source of the earthquake. However, in the case of Mexico City is a sediment-filled basin surrounded by bedrock mountains. As waves progress and move toward the softer bed, basin amplification occurs, that is having low frequency and high amplitude. You can see here, at far this is high frequency, low amplitude, but at the basin amplification, there is increase in magnitude and duration. As waves progress and move toward the softer bed, basin amplification occurs, having low frequency and high amplitude. This has shaken the soft sediments of the ground like a jelly in a bowl. Natural period of different buildings is shown, which represents difference in resonance period of buildings in Mexico City. This is a low-rise building, a high-rise building, this medium-rise, 2 seconds period. So in the case of Mexico earthquake, these buildings got damaged. In Mexico City earthquake, as the ground was oscillating at 2-second time period, the building of 8 to 20 stories with similar natural period, that is around 2-second natural period, suffered the most damage. So these short buildings withstood, very high buildings also withstood the earthquake, but these medium-rise buildings 2 seconds period, 8 to 20 stories building, they got damaged. So it not only subsoil conditions cause this kind of damage. Some of the photographs, most of the earthquake damage to the buildings, the two reasons are the resonance in the lake bed sediments and the long duration of the shaking. Actually, Mexico City had one of the most stringent building codes based on experience gained from earthquakes, which happened in 1957 and 1979. However, still a lot of damage occurred during this 1985 earthquake. In some cases, damage was caused by the adjacent building banging against the walls. We call this pounding. Then some foundations experienced damage such as pile driven into clay, which was held in place by friction, turned out to be weak. It was not driven up to hard ground, so it was taking the load through friction only, so which was inadequate in the present case. That was about Mexico earthquake. Some photographs here, 1988 Armenia earthquake. This is unreinforced masonry building. Large scale damage has occurred. This is 1992 Turkey building, Turkey earthquake. This is reinforced concrete building. Damage, severely damaged, nearly collapsed residential building complex. Many failure forms, such as column shear, joint shear, lack of bar anchoring to the concrete frame members. You can see in this example. Then 1995 Kobe earthquake in Japan. The earthquake occurred early morning. So a lot of damage occurred because of the fire. People were preparing breakfast and using fire. So this fire spread very fast. Aerial view of the city devastated by the first earthquake fires. By the time the fires died out, large areas of Kobe had been destroyed. Then this is earthquake. An elevated expressway, Hanshin Expressway, has collapsed here. Closer view. Just after a few days, earthquake happened January 17th, 1995. Few days after they started restoration.
Sir, your voice is not there. Hello, sir, your voice is hanged up. And BBD is also hanged up.
Locations.
Yes.
Hello?
Your voice is something interrupted. It will be hanged up. So now it is okay. Hello. देवी देवी क्या ख्याल आई
Hello?
Hello, sir.
Hello, are you able to hear me? Sorry about this.
Not an issue, sir. I am able to hear you, sir. But during presentation, you just switch off your video so that the net will be captured less, sir.
Okay, okay, okay.
Okay, sir. Okay, sir.
Now I switched off the video. I started Taiwan earthquake, Chichi earthquake. Were you able to hear that? I don't know when I lost the connection. Hello? Hello?
Hello.
Can anybody tell me?
Yes, yes, yes. You may start from Chichi earthquake.
Chichi earthquake. Okay.
Yes. Okay.
Thank you.
Welcome, welcome.
This is 1999 Chichi earthquake happened in 19 September 21, 1999. Shallow focus earthquake, only 8 kilometers the focal depth. So large scale damage happened here. Magnitude 7.3, vertical displacements reaching about 7 meters. 2,400 people died and 10,700 people injured. Main shock accompanied by more than 10,000 aftershocks. And the peak ground acceleration was 1 G, 1 to 1.2 G. Some of the damage pattern here, you can see a ground story has been crashed. 51,711 buildings destroyed, 53,000, more than 53,000 severely damaged. Commercial buildings with soft story at the bottom, complete collapse of the buildings close to the fault line was observed. This is failure of a dam, suffered partial collapse of a buttress and the breach deck at the mid crest area. Here, damage to bridges, roads, railway lines, and so on. Movement of embankment behind bridge abutments, landslides destroying roads, railway lines got bent up and twisted. Structural damages, compression failure of column exposing reinforcement at the base. Here, two columns are there. Left column is embedded in lintel beam whereas the right column is independent and undergoing local burning. The upper portion of the building undergone 90-degree rotation and crashed onto the ground. It happened due to the crashing of columns on one side at the ground story. And here shear cracks on the walls in the form of 45-degree. We saw earlier also these kinds of X-ray cracks. Then it was during the damage survey, it was observed absence of quality control. Use of more than 20% fly ash in ready mix concrete, aggregates of improper size and gradation, you can see here, and use of underground sand contaminated with clay and organic matter, and adding excess water to increase workability and reduce labor hours. So these were some of the causes of failure in concrete. Absence of quality control. And in the case of steel, tension test on a rebar from the damaged building showed very small elongation and very little necking, indicating low ductility. And corrosion was also observed in the reinforcement of slabs, which may be attributed to thin concrete cover provided or use of the steel tank. Other structural damage example, the building code require not more than 50% of the reinforcement to overlap at a single section. Many buildings failed at section where 100% of rebar overlap took place. So we should not provide these kinds of practices, more than 50% of rebars overlapping. Then the ties used in the column were provided with simple hooks or two U-shaped bends close together. Ties should be made with 135-degree bend, 135-degree hook, and 6 times the bar diameter extension at the free end. That was not observed in many failure cases. Then spacing of stirrups. The hoops spacing was another common code violation. The presence of conduits in the column reduces its effective area. You can see here. These kinds of conduits for electric and other electric cables and similar utility purposes, many times they will reduce the effective column area and increase the possibility. This is 2010 Haiti earthquake. Haiti is in Central America, epicenter Port au Prince, magnitude 7, focal depth 13 kilometers, duration 30 seconds. More than 2 lakh people died. Airport, school, hospitals, etc. got damaged. Haiti is a poor country in Central America, the poorest country in Western Hemisphere, and many times there are no enforcing of building codes. The causes of failure here: X cracking of the walls, X cracking, shear cracking, localized damage, column shear failures, and toppling and out of plane wall failures. Some of the damaged photographs: poor aggregate shape and grading, poorly located construction joints, formwork embedded in finished concrete. Formwork embedded in finished concrete. These kinds of poor construction practices, quality control. Formwork embedded in finished concrete, debris left in joints, segregation, voids, and of course honeycombing. These are some of the causes of failures. This Haiti earthquake. Then 2011 Tohoku earthquake in Japan. A major earthquake occurred in the Pacific Ocean of the coast of Miyagi, Japan on March 11, 2011. At a magnitude of 9, it was the largest recorded earthquake in Japan since modern seismograms became available. Huge physical damage and loss of life. Total deaths were 19,007 people, in addition to 2 lakh, 2559, 2,559 people missing. This earthquake was secondary damage, nuclear damage to nuclear reactor, caused a severe accident at the Fukushima Daiichi nuclear power plant, which was the second worst nuclear catastrophe after Chernobyl disaster. So this is Miyagi Prefecture. This is this star. A star here shows the source of the earthquake here, and the nuclear reactors, Fukushima, Daiichi, and Dain, number 1, number 2. These 2 nuclear reactors were damaged. And there was radioactive contamination also in this region. Building damage due to site-specific ground motion amplification in Aboyama Hill in Sendai. This is actually a civil engineering department building of Sendai University. A 9-story building housing the departments of civil engineering and architecture in the Faculty of Engineering at Tohoku University. This building got damaged. This building was constructed in 1969 and seismically retrofitted after the 1978 Miyagi earthquake. There was a severe earthquake nearby, 1978. After this building was retrofitted. The building was on a hill slope site and has a foundation with the reinforced concrete cross piles of length 12 meters. RC piles of 12 meters length were provided. And in this building, long-term monitoring of dynamic characteristics has been performed by instruments for 40 or so years, 40 plus years, since the building was completed. Building was completed in 1969 and they were monitoring the dynamic properties of the building. And this building was heavily damaged at the bottom of the 4 columns, at the bottom of 4 corner columns. So at the 4 corners of this building, shown here, okay, this damage here, damage of corner column. The severe crack in the side shear wall was possibly due to partial uplifting at the level of the 3rd floor. Shear wall, there was damage, cracks developed in this shear wall also. This may be due to the uplifting at the level of the 3rd floor. So this instrumented building of civil department also got damaged, mainly damage to the 4 corner columns. Then other building damage examples are shown. Damage to a non-structural wall, infill wall. Damage to non-structural wall, again shown here. Cracks developed. Here crack to a beam, structural beam, load-bearing beam. Crack has developed. This is a 4-story building, inclined 4-story RC file foundation building. A subsided bottom part of the southeast corner column. So this column has subsided. And uplifting of the foundation in the north side. So southeast side corner column subsides, and the other side you can see here, north side, there is uplifting of the foundation. Then during this earthquake, which occurred, epicenter we saw here, epicenter of the earthquake. So this resulted in tsunami, created tsunami, and lot of damage occurred along this coast due to tsunami. Concrete wall failure due to internal pressurization, uplifted and overturned 2-story RC building. What we are seeing here is the bottom side of the RC building. Fish market building damage. Cracks developed in the building and also uplifting damage. And as I mentioned, this earthquake caused nuclear disaster. Fukushima Daiichi nuclear reactor. The earthquake caused shutdowns and other electrical grid supply problems. The reactor's electricity supplies failed and their emergency diesel generators automatically started. So when the earthquake happened, there was automatic shutdown of electrical power supply. Then diesel generators started and they supplied powers. These provided critical electrical power to the pumps that circulated coolant through the reactor's cores. When generated arrived shortly afterwards, it flooded the lower parts of the reactors, causing the failure of emergency generators and loss of power to the circulating pumps. So, earthquake, these buildings were safe. However, when the tsunamis came, the height of the tsunami was more than what they had planned while constructing this facility. So these tsunamis inundated or flooded the lower parts of the reactors. So the power generators, they failed. So there was loss of power to the circulating pumps. The resultant loss of reactor core cooling led to nuclear meltdowns, hydrogen explosions, and the release of radioactive contamination between 12th and 15th March. So earthquake happened on 11th. So 12th and between 12th and 15th, there was release of radioactive contamination. So you can see here damaged building at Fukushima Daiichi nuclear power plant. They had evacuated more than 1 lakh people when the damage to radiation. So in the Fukushima, the Sendai earthquake, there was damage due to earthquake. There was damage due to tsunami, which occurred due to the earthquake. And then also there was damage due to this nuclear radiation. Damage to the nuclear facilities. This slide shows the 2015 Nepal earthquake, magnitude 7.8. Nepal earthquake. Areas of strong shaking in Nepal and also parts of India, northern parts of India. This was the epicenter and there were many aftershocks. Nepal has many masonry buildings. So many such buildings were damaged due to this earthquake. Then fissures on the road and also damage to RC. Nepal earthquake magnitude 7.8. Then this is Indonesia earthquake, 2018 Sulawesi earthquake in Indonesia. On September 28, 1802 local time, a strong earthquake of magnitude 7.5 struck central Sulawesi province in Indonesia. The Sulawesi province. Focal depth was 20 kilometers. This earthquake triggered landslide and tsunami in many parts of Palu and Donggala region. This is Palu region here. Intensity distribution map is shown here. The locality had 3 general types of low-rise construction. Stilt timber houses built on stilts. Timber frame with the mortar infill and confined masonry, clay brick and concrete block. And these buildings, many buildings withstood the earthquake, but they got damaged because of tsunami. A masonry school building failed here. Out of line failure of a timber frame structure. Masonry wall damage to insufficient confinement. And then large ground displacements led to damage of road. So here you can see the moment, lateral moment. This is 2018 Indonesia earthquake. I think I have covered some of the major earthquakes so far. Happened starting from the Chile 1960 Chile earthquake, then Alaska earthquake, Bhuj earthquake, Tohoku Japan earthquake, and then Niigata earthquake, and so on. So some of the damage patterns during these past earthquakes we have discussed. Now some slides about the ductility aspects. Why lightness and ductility in earthquake resistant design? Lightness, earthquake force is a function of mass. So to reduce earthquake force mass into acceleration, which is the inertia force. So to reduce inertia force, either we have to decrease mass or decrease the earthquake, acceleration. To decrease mass means to make the structure as light as possible. If a structure is ductile, it has the ability to absorb energy without critical failure increases, allows a structure to undergo large plastic deformations with little decrease in strength, and have the ability to sway back and forth during an earthquake and to withstand earthquake effects without collapse. So our objective is to make the structure light and make it as ductile as possible. Severe earthquake motions result in the case of brittle structure, there can be sudden failure. And if the structure is ductile, it can undergo inelastic deformation and there can be absorption of energy. This figure shows schematically force versus deformation. This is a brittle structure, this dotted line brittle structure. So failure is sudden, whereas this line shows the ductile structure. Ductile, so it undergo large deformation before failure. So this is the displacement, deformation at yield, and this is at the ultimate. And to increase ductility, for example, to prevent the shear failure, we provide lateral ties or stirrups at closer intervals. Effect of spacing of transverse steel on efficiency of confinement is shown here. So by providing at closer intervals, we can increase the confinement. The requirement of greater ductility in earthquake resistant design of buildings is a feature that is different from conventional design of buildings for gravity loads. So in conventional design, when we don't consider earthquake, we are not much bothered about the ductility aspects. The observation during past earthquakes, well-designed and detailed reinforced concrete structures survived severe shocks, and majority of failures due to faulty design practice and lack of detailing for ductility. So measure of ductility. The available ductility of a given structure is not precisely a defined quantity. It depends on the type of structure, the redundancy, the material of load carrying system, and the intensity of applied vertical loads. It is expressed for whole building, or it can be for a member, cross section, or for material, and is quantified by a ductility factor. Displacements, member end rotations, and section curvatures, these are typical variables to use to express ductility. While it is generally sufficient to provide adequate stiffness and strength in designing buildings for wind loading, a third basic requirement of ductility is necessary in the design of earthquake resistant structures. The requirement of ductility arises because it is not economical to design buildings to respond elastically to moderate to strong earthquakes. So when we are having severe earthquake, we expect that the building responds inelastically. To ensure ductility, the design engineer must follow certain basic design concepts and follow detailing practices in members and also in joints. The structure to deform in a ductile manner without significant loss of strength through a number of cycles of displacement response. This allows the structure to absorb a major portion of energy from an earthquake without significant damage. So by limiting the demands on ductility factors, we can control the extent of damage. Some of these photographs we have taken from the ductility code, design and detailing code, IS 13920. In an external joint, this I showed in the case of one building in masonry building in Bhuj, which got damaged in Bhuj earthquake. In external joint, both the top and bottom steel of the beam shall be provided with the anchorage length beyond the inner face equal to LD, that is development length, plus 10 times diameter minus the allowance for 90-degree bends. So this length here, this is inner face. So this length will be 10 times the diameter of bar plus development length, LD plus 10 diameter bar minus the allowance which we provide here for the 90-degree bend. So it is same for bottom bars. Bottom bars also development length plus 10 times the bar diameter. So we need to provide in the external joint these facilities. And then in the web reinforcement, these 135-degree hooks. Web reinforcement shall consist of vertical hooks. A vertical hoop is a closed stirrup having 135-degree hook with 10 times diameter bar extension, but not less than 75 mm at each end, that is embedded in the hoop. 2002. In the recent revision, this value is 65 mm, I guess. The hoop shall engage peripheral longitudinal bars. This is shown here. You can provide 135-degree hook like this, or you can also provide a hook cross tie, as you can see here. And this length is 10 times the diameter, more than 75 mm. And then splicing. Not more than 50% of bars should be spliced at a section. We saw one damage pattern in Taiwan earthquake, how all the bars were spliced at one location, that is 100% splicing, which is not recommended. Not more than 50% of bars should be spliced. And we have, when there is splicing, we provide here stirrups at closer intervals and spacing not more than 150 mm, not more than 150 mm. And this length not less than development tension. And then this is beam reinforcement. We have these vertical ties or stirrups at close intervals, closer to the joints. So this is for a length of 2 times the effective depth. These effective depth of the beam. So from the beam, from this column face up to a length of 2D, we have to provide stirrups or vertical ties at closer intervals. Same thing is shown here. Then minimum 2 bars for full length along top and bottom face, and reinforcement to be provided is specified here. Then transverse reinforcement is column, similar to beams. Here also we provide 135-degree hooks. And when this spacing is the size of the a column is such that the distance is more than 300 mm, in such a case we need to provide cross ties. And if the dimension is more than 300 mm on both sides, then we need to provide these cross ties on both directions. And this is column and joint detailing. Even in the case of columns, this lapping specifications are given in IS 13920 and also at the beam column joints, where we need to, near the face of these joints, we need to provide lateral ties at closer intervals. This is provided in this IS 13920, so that section number is mentioned here. So special confining reinforcement we need to provide to achieve ductility. A confined joint with beams framing into all four sides, confining reinforcement as per this clause. Then provision of special confining reinforcement we need to provide in footing also for a depth of greater than 300 mm, closely spaced intervals. So those are some of the examples to provide ductility or considerations of ductility for beams, columns, beam column joints, and footing. Maybe in other lectures also you have been introduced the earthquake resistant design philosophy. Severity of ground shaking at a given location during an earthquake can be minor, moderate, and strong. Minor shaking occurs frequently, moderate shaking occasionally, and strong shaking rarely. Earthquake proof is too expensive to make a structure to withstand the earthquake, which may occur in once in 100 years, once in 1,000 years. Such a earthquake proof approach is too expensive, is not practical. So our objective is to make it earthquake resistant, and it is such that in the minor earthquakes there are no damage to the structural elements like beams, columns, slabs, which are load carrying elements, and no damage to non-structural elements also like infill walls, chedjas. So such non-structural elements also there is no damage during minor earthquake. During moderate earthquake, no damage to structural elements, but there can be some damage to non-structural elements, repairable damage to non-structural elements. And in the case of major earthquakes, severe earthquakes, there can be some damage even to structural elements. There can be cracks in beams, columns, but the structure as a whole should not collapse. We should be able to save the lives of the occupants. And there can be substantial damage to non-structural elements. So this is so-called earthquake resistant design philosophy. So we classify into minor earthquakes, moderate earthquakes, and major earthquakes. Even in the case of major earthquake, there should not be collapse of the structures. We should be able to save the lives. And this is just slide. Earthquake resistant design code of practice IS 1893. It has been revised many times, and the latest revision is in 2016. Based on past experience, we revised the code, and there are 5 parts. Part 1, general provisions as well as requirements of buildings. Part 2 is for liquid retaining tanks, elevated and ground supported. Part 3 deals with bridges and retaining walls. Part 4, industrial structures, including stack-like structures. And Part 5, dams and embankments. That is earthquake resistant design code. There are many codes. I am just mentioning here 2 codes, mainly for RC building. Ductile detailing. of RC structure subjected to seismic force. This is explained in this code. Very important code, IS 13920, and the latest revision is 2016. So in this way, I explained some of the damage, structural damage during fast earthquakes, and also some of the ground failure, the liquefaction effects on veterans. I think this is the last slide. Yeah, this is NITK beach. I don't know any of the participants have visited NITK. It is along the west coast of Karnataka, our campus. This is our campus. We have a beach gate somewhere here. So although beach does not belong to NITK, it's government's only, but we say NITK beach. There is a lighthouse nearby. We can climb this lighthouse and have the view of this, beautiful view of this Arabian Sea. So thank you very much for your kind attention. I also thank the organizers for giving me this opportunity to make a presentation as part of this activity. Thank you, sir. Hello?
Yes, sir. Okay. Thank you, sir, for your kind presentation. Now, I think we invite a couple of questions. We have, few minutes remaining still. I think the participants are requested to put the question on chat box, so we can ask the sir. Or you may have a question, put a question on WhatsApp group also. I will dictate the same.
My email ID is there. If anybody wants to contact me later, also you can use this email ID, katta@nitk.edu.
So I request to the participants that if you have sharing your questions or doubts over here at this platform, let us take the advantage of the sir. If you have, please ask the questions. Sir, one participant has asked the question.
Yes, sir.
Where time history analysis will be beneficial? Under which circumstances?
Time history analysis is useful when we are dealing with a specific earthquake. If we know the earthquake data for a given location, based on that, if you want to design, we can do the analysis using time history. As you know, the earthquake varies from place to place, also depending on the ground conditions. For example, if you consider the plotting of Bhuj earthquake with another Taiwan earthquake, or say Niigata earthquake, there will be a variation in the frequency content and also the amplitude and so on. But if you are considering the specific characteristics of a given location, for example, if you are constructing in Bhuj area and you know the Bhuj earthquake and you also have some records of the previous earthquake, then you can use that as the input as to the design. And for specific structures like dams, which are going to be constructed in a given location, and if you have the seismic characteristics of that region. If you know that, then you can input the earthquake data and do a time history analysis.
Thank you, sir.
Also, we can incorporate nonlinear characteristics of the building better in non-linear time history analysis.
Participants have asked one another question: that should the cantilevered beam or slab to be omitted for earthquake resistant design?
Cantilever slab we can design. We can design for earthquake loads, no problem. Where we give the reinforcement, when we provide the reinforcements, we should be extra careful. We can design open ground story also for earthquake load. That is no problem. But we have to take into consideration. We have to design for a higher force in those areas.
Okay. Sir, another question is that when we are designing for any structure by using time history method,
Hello?
we got the different modes. So up to how much mode?
Hello?
Hello, my voice is clear? Hello? Whether I am audible, sir? Hello, whether I am audible?
Yes, sir.
Okay, now a question which has been asked that while we are designing a structure and analyzed by time history method, we get numbers of modes.
Vibration modes.
Hello, numbers of modes in a structure. So up to how much mode we have to go?
Hello?
Hello, my voice is there, sir, with you?
Yes, sir.
Sir, have you listened to the question?
We have to input the earthquake data for different modes and we have to compute the response in that mode.
No, the question is that up to how much mode we have to apply?
Usually, lower modes contribution is more. When we consider the response of the structure in considering different vibration modes. For example, if you consider 10 degree of freedom structure, there will be 10 vibration modes and there will be response contribution, first mode, second mode, third mode, and so on. But usually lowest mode, first mode almost 90%, then second mode about 4%, third mode about 1%, and so on. So lower few modes, if you consider for the analysis, that is sufficient. About 90% has to be captured.
Okay, sir. Another question: can we consider masonry wall stiffness in seismic assessment?
Masonry walls we can consider, sir. We can consider.
Then how it is effective?
No, there are so-called strut, considering infill as a strut. Are you referring to the infill masonry in RC building?
Yes. It's the same one, same question.
We can consider as a strut, and it will contribute.
So in case of strut, how the stiffness has been calculated?
Which considers the thickness of the masonry wall, then elastic properties, Young's modulus, height, and so on. There are a formula available. We have to incorporate the various parameters in that formula, and we get the stiffness. It can be incorporated.
Yes. Sir, one question is that lightweight ACC blocks in masonry will be beneficial?
Lightweight masonry, we can use it. Infill walls, we can use light material. Yes, sir.
So, sir, there is no more questions from the participants. So, on the behalf of the participants, I'm thankful to you to enlighten us, sir. It is really our pleasure that to sparing the time with us and devote your precious time for this FTP. Once again, thank you, sir. So I kindly request you to share your PPT to me on personal mail so that I can share the same thing to the participants.
Okay, sir. I will send now itself. Thank you.
Thank you, sir. Thank you, sir. Now, all the participants are requested. The third session will be started at the 3:30. So we will meet at 3:30. The session will be started at 3:30. Thank you very much. Thank you.